Hello, Gershonis. I wanted to try a new format to answer your questions, so I hope you can bear with me, and hopefully this will be a bit more informative than just answering the questions via email. So stay tuned. Okay, guys, so before I get started, I thought it would be appropriate to give you all a crash course in sidewall fusion. Um, so right there is our Sidewinder tool that we're using to actually perform the fusion. And this is a heater with both a concave and convex faces. So the heater I have set up presently for 8-inch. These are the 6-inch, so I'm just showing you these to make it very clear that there are two sets of faces. So 6-inch and 8-inch is on the tool. They're very much specific to the size main that you're using. Before I get into the details about how our fitting is being fused, I want to first make sure that you guys understand how normal fusion is performed. So first things first, you're going to get your tool set up on the location. Make sure everything is level exactly the way that you want. The nice part about this fixture and the way that it works with normal fittings is that it 100% definitively locates where that fitting is to be fused. There's no variation once you've locked this tool down in place. It's going to be totally a repeatable process. So that part's important. Got everything tightened down, and I have already cleaned and prepped the surface, but that would be the next step. So I'll just show you the heater side of things. So ideally, you have a heater face, both concave and convex, that match the size of the fitting. Obviously, this face is much larger than needed, so we're going to be heating a lot more pipe than is strictly necessary for this fusion, but this is the only 8-inch face that I have to work with right now, so we're going to go with that. So the first part of the process is what they call the bead up, and that's when you apply significant amount of pressure and wait until you've seen a bead form all the way around the fitting and the pipe. So I don't care where, it's going to start somewhere and work its way around, but as long as you've got good contact all the way around, which I'm still waiting for, then you let off. There's no pressure at all other than gravity on this thing at present. So in order to get a good bead up, that it's very important to have a radius that's matching, and you guys have done a great job with the machining, so that seems to be working well. The bead up never occurred with our old fittings. They were just the face here was too uneven. You might sit there for 5 freaking minutes waiting for a bead up when a normal bead up on any other fitting is going to take certainly not more than 30 seconds. You're never going to run into a fusion operation where your bead up should take longer than that, because these radiuses should match. It's really just a matter of making an impression in both the fitting and the pipe. So now we're in what's called the heat soak portion of the fusion. And since this is just for demonstrational purposes, I'm going to pretend that we have fully heated the fitting. So I'm going to take this out, put that down, and apply pressure. Now, if you could tell, if I let go, the pressure actually slowly goes down because just the way that the material works. So you have to stay on top of it to keep it at a consistent pressure. So, of course, I won't know exactly what these pressures will be until I have finished fittings to work with. But this, at least the way that you just seen it, that would need to sit for about 10 minutes before I could safely remove this and move along to the next fitting. Maybe more like 5 minutes, but um, certainly you do need to spend some time with the heater, or sorry, the fixture in place on location after fusion has been done. So another important thing to point out is that with normal fusion, you're doing your drilling of the hole afterwards. Obviously, in our case, that's not a possibility. I certainly don't know of any way from drilling inside, so that means that we have to pre-drill before the fitting goes on. So at present, I do not have a nice, neat, and repeatable way of holding on to this fitting. So my carriage can provide me with the appropriate pressure, but I'm totally eyeballing the location of the hole and all of those factors at present. So that's intro to sidewall fusion. I'm going to go ahead and move on to your questions. In order to keep the video down to a reasonable size, I'm inserting the question just for a second. So you're going to want to pause it to read the question, and then of course directly after I will be answering the question. So pause it for as long as you need to read the question, and then go ahead and listen to my response. The radius of the 6 and the 8-inch seem to match the heater face quite well. You can see there's a little bit of a gap there, but it's not really too bad, nothing that would be terribly significant after the bead up portion of the heat cycle. Eight-inch is the size that we're fusing today. The heater face radius is definitely main size specific. So here in my hand is the 6-inch heater face that we're using for our testing purposes, and here is the 8-inch. Now it's also important to note that these heater faces here are much larger than we would actually require for our production process. So this is actually appropriately sized for a 4-inch saddle. These heater faces are sufficient for our testing purposes, but it's important to note that we're going to want to have purpose-built heater faces so that the amount of surface area of the fitting is matching the amount of surface area that we're heating on the pipe, rather than having a whole lot more heat going into the pipe than actually going into the fitting. So these are no longer going to work for us because this was back when we were taking the combination socket and saddle fitting, but it's the same principle. We need heaters that match the surface area of the fitting to the surface area of the pipe. So beyond matching the fitting up to the heater face and just kind of checking out that gap, I have no way of measuring or verifying the radius imparted on this fitting. In terms of leading and trailing edges, as far as this fitting is concerned, as you pointed out, the mold needs to be thickened in this area to be much more similar to something like this, which I believe this is actually the fitting that I measured when I determined how thick we should make that leading and trailing edge. So it's definitely lifting up when it's being put up against the heater face, so it's just not thick enough to handle the heat that's being put into it. Okay, so I've thought about it, and I'm reconsidering my inclination to machine a smaller radius on this surface to accomplish full contact with the heater. The main problem here, as we pointed out, is the thickness of this face. That's about to get substantially thicker. None of the other manufacturers are doing that, they're all matching the radius of the heater, so they're not under or overshooting it. They're matching it exactly. They're just designing a fitting that's sturdy enough to withstand the fusion forces. So that needs to be our goal, is create a fitting that's got the appropriate thicknesses so that it can hold up for the entire fusion process. And I think that we should start by matching the radius as closely as we can, and you guys have done a good job with that on these fittings. In the next slide here, I'm going to show you guys a table that I put together to compare the relative thicknesses of leading and trailing edges. So of course we've got the existing machine fitting. We're going to compare that to the current model or proposed model, and then I'm also going to include for reference a similar fitting, and we'll go ahead and switch over to that table view right now, but this is what I'm measuring. So get ready to press pause. As you can see from this table, our current fitting design is substantially thicker than the machine fitting at present, but also this fitting here is quite a bit thicker than the design fitting, so it may be worth reconsidering making the base even thicker than the model currently suggests. So I'm actually going to redraw the fitting as a separate version to illustrate a substantially thicker base, because I think the thicker the better. We match the radius here via machining exactly to the heater tool, and then we'll definitely have enough rigidity to counteract any of the leading and trailing deflection issues that we're experiencing presently when the fitting is being heated. With regard to the 135s, I did not actually bother to fuse these guys. To me, this looks exactly like the fitting that Versa had issues with, or in other words, the first fitting that we had come out with. So there's a tremendous ovality issue here, and whether they seated or not, it wouldn't be safe to, I think, continue moving forward with 60 thousandths out around, something on that order. So I think you guys have proposed thinning this out, which would change our shrinkage issue and hopefully provide us with a much more round fitting to be socket fused to. With regard to leading and trailing edges and other saddle fusion fittings, the answer is a definite no. I've never had an issue where a saddle fusion fitting would roll back on the leading or trailing edges. Obviously this fitting is a substantially different design. There's very limited room for any type of deflection on that edge, and even in this case you can see that the fitting is very substantially thick in the area where the deflection is occurring. So we may want to consider with our fitting, obviously we've already drawn it up as it being a bit thicker, but we may want to be real sure that we have enough material to prevent there being any type of deflection. It's really difficult for me to give you an apples to apples comparison, old fitting versus the new one. The old fitting obviously was a combination socket and saddle. We tried to pick a time that would be appropriate for both, which there really isn't one because they needed to be heated separately. But anyways, so let's say I was using 45 seconds heat cycle for these, and the inside of the pipe, the hole wasn't quite as significantly melted closed as with the new method, but the new method with the saddle is going to require, I don't know, forget 45 seconds for our compromise on the latest one. I'm going to say about a minute to a minute and a half per joint in terms of heat for this guy here. So he's going to take a lot more heat. We're going to need to compensate for that. I think perhaps by having a larger hole to start with. Also, I'm going to draw up a version that has a chamfer on the inside so that we've got some place for that extra melted material to go. So between making the hole perhaps a bit larger and that chamfer should give the material some place to be that's not actually constraining the diameter of the finished fused hole.